Hey Extension 2, thank you for joining me for another video lesson. We're starting off with a flashback from the 2017 HSC exam. We've got a multiple choice question. We've got an Argand diagram with complex numbers Z and W. Z's in quadrant 1 and W is in quadrant 2. Which of these four complex numbers is going to lie in the third quadrant down here? Pause the video, see which one you would be picking as your answer. Okay, let's work through all of them. So for the first one, negative W is going to reflect us through the center point and put us through into quadrant 4. So we're changing the real part and changing the imaginary part. So we're at quadrant 4, not quadrant 3. Okay, option B, we're taking Z and we're multiplying it by I, which will rotate us 90 degrees in the anti-clockwise direction, putting us into the second quadrant. And then multiplying by 2 is just going to double the length of that vector. So the second one is going to be in quadrant 2, which is not what we want. Option C is Z conjugate. So we saw last week that the conjugate of a complex number is going to reflect across the real axis. So Z conjugate will be down here in quadrant 4. So it must be option D. What do we know about W minus Z? In last week's video, we saw that W minus Z is going to be represented by the vector from Z to W, which looks like this. Now, if we wanted to point to a complex number, we place that, that vector starting at the origin, like this. And now that point right there is going to be W minus Z, which is in the third quadrant. So it is option D. Well done if you selected that as your answer. Okay, for our third lesson in complex numbers, we're looking at modulus and argument. Okay, so last week we saw how complex numbers can be represented as coordinates using Argand diagrams. So for an example, this dot right here is 2, 2, representing the complex number 2 plus 2i. It's got 2 on the reals and 2 on the imaginary axis. But we can actually think of this position here in a different sort of geometrical way. We can say, yeah, this is the coordinate 2, 2. We could also say this is a point that is 2 root 2 units from the center point, from the origin. Okay, so we get that figure by doing some Pythagoras. So 2 squared plus 2 squared is 8. And then we do the square root of 8, which is 2 root 2. Okay, so we can find that distance from the center using Pythagoras. We can also think of it in terms of how far this vector has been rotated from the real positive axis. Okay, so we could say that this point is representing the complex number 2 plus 2i. Or alternatively, we could also say that the complex number 2 plus 2i is represented by this blue vector, which has a length of 2 root 2 and an angle of rotation of pi over 4. Okay, so it's two different ways of thinking about the same complex number, just in two different types of geometry. So this blue distance from the center, in complex numbers, we refer to this as the modulus of the number, and the angle of rotation, we're going to refer to it as the argument. Why do we call this the modulus and the argument? That's a really good question. Okay, so here's our point for our notes. We've got x plus iy, x on the reals and y on the imaginary axis, and here is our point. So like we said, the modulus is the distance from this point to the origin of the center point. Okay, so we're going to denote this as either z with absolute value signs around it, or occasionally we'll use a letter r. All right, the way we calculate this, like we said, is we do Pythagoras. So we have x squared plus y squared equals, and then we square root it, and we've got the modulus. The reason we're using absolute value notation, in the advanced course, you were taught that the absolute value of a number is typically representing its distance from 0. So for example, the absolute value of -3 is 3 because it's 3 units from 0. And we're essentially doing the same thing here. Okay, so the absolute value of a complex number is the distance from that point to the center, which is 0, 0. So it's the same thing, but because we have 2 dimensions, it's a bit more complex, I suppose. Okay, and the argument, like we said, that's going to be our angle, always from the positive real axis. So it's going to be our theta right here. Our notation for this is going to be arg z, which is argument of z, or occasionally we'll use just theta as a shorthand. Now, important thing about the argument of a complex number is it has to be between minus pi and positive pi. What that means is if we had a complex number in the second quadrant, we would measure from the positive real axis and we get an obtuse angle. All right, so we measure from positive real, we go anti-clockwise until we hit 180. We don't keep going into the third quadrant and use reflex angles, okay? What we do is we measure from the real positive all the way up to 180. If you want to measure in quadrants 3 or 4, you've got to go backwards, as in clockwise, from the positive real axis. All right? What this means is, in the first 2 quadrants, we'll have positive arguments, and in the third and fourth quadrants, we'll have negative arguments because we are rotating in the opposite direction. Takes a bit of getting used to, but it's just the same thing, but either forwards or backwards, essentially. All right, let's now talk about what's called polar form of a complex number. So we're going to start off with this triangle here. We've got x, y, we've got r as the modulus of the number, and theta is, of course, our argument. Now we're going to do a bit of trigonometry here. So we know that cosine of this angle theta right here is going to be the adjacent side divided by the hypotenuse. So we're going to write cos theta is equal to x over r. Okay, now we're going to multiply that r across to the left-hand side, and we have x equals r cos theta. So we have an expression for the real component of the number in terms of r and theta. We'll do a similar thing with y. We need to use sine theta because sine is opposite over hypotenuse. So sine theta will be y over r. Multiply the r across, and now we have that the imaginary part, which is the y, is going to be equal to r sine theta. This means we can take our complex number, which is normally written as x plus iy, and we can substitute x and y as these two forms here. So we have z is equal to r cos theta plus I times r sine theta. We factor the r out the front of the expression, and this is called the polar form of a complex number. Okay, so we're expressing a complex number in terms of its distance from the center and its angle of rotation. So 2 different ways of talking about the same point or the same complex number. And we call it polar form. Okay, it's occasionally also called mod-arg form. So in the previous version of this course, we called it mod-arg form for about 30 years. Now in the last couple of years, we want to start talking about it as polar form, which is more standard at universities. Okay, sometimes this can be a bit annoying to write out because it's a lot of letters and mathematicians are lazy. So sometimes we're going to abbreviate this as just r cis theta, so cos I sine theta. So this right here is the exact same thing as this, just in shorthand. All right, cool. Let's have a go at some practice with expressing complex numbers in polar form. So for these 4 complex numbers, we want to find their modulus and their argument. So we can write them in this form in the blue box right here. Okay, now there are ways of finding the modulus and argument if you have the right calculator, which I'll show you guys in class later on. But for today, we're going to do all things the old school way, which is by drawing a picture. Okay, you got to get really comfortable with this because this is like a bread and butter extension 2 type question. Okay, let's draw the point -1 positive root 3 to represent this complex number. All right, it doesn't have to be perfectly to scale, but as long as you have a roughly good looking triangle, it does make the geometry a little bit easier. So we're going 1 to the left and we're going root 3 up, and here is our triangle. Okay, now let's find our distance from the center. So let's do some Pythagoras. So root 3 squared is 3, 1 squared is 1, add them together and you get 4. And so this line here must have a length of 2 units. So the modulus of this first complex number is 2. Now, is this triangle familiar to you? 1, 2, root 3. It should be. It's one of the exact value triangles that we use in the advanced course, and it's on your formula sheet. So if you're really familiar with this triangle, you know that this angle inside here is going to be 60 degrees. However, we don't want this angle because, as we said, the argument is measured from the positive real axis. So from this positive x line, the angle around to our blue vector is going to be 120 degrees. Okay, so 60 inside our triangle, 120 outside of our triangle, which if we write it in radians would be 2/3 of pi. So here is our polar form. We've got our modulus out the front, a distance of 2. We've got cos I sine, and our angle is 2 pi on 3 because this blue vector is 120 degrees anti-clockwise from the positive real axis. Okay, so you never want to have these angles here as degrees. We're always working with radians for these ones. Okay, let's do the next one. So we've got root 2 minus 2i. So if we draw a picture once again, We're going to go root 2 across and then root 2 down, and here is our complex number. Okay, now we have a picture. Let's do some Pythagoras and figure out the distance from the center. So if we square these two, we get 2. If we add them together, we get 4. And if we square root it, we once again get 2. So just like in question A, our modulus is a unit length of 2. All right, now what kind of triangle do we have here? Because both of these two sides are the same length, this is an isosceles triangle, which means both of these two base angles must be 45 degrees. Okay, however, because from the positive real axis, we are measuring in the clockwise direction, for angles, that's what we define as a negative rotation. So our argument is not going to be 45 degrees or pi on 4. Our argument is going to be minus pi on 4. And so here is our complex number in polar form. We've got a modulus of 2. We've got an argument of minus pi on 4, which is 45 degrees in the negative direction. Okay, so once again, quadrants 1 and 2 will be positive. Quadrants 3 and 4 will have negative arguments. Okay, question C is a bit of an easy one because it's only got an imaginary component, so the sketch is a bit simpler. So minus 3i is just 3 down the imaginary axis. So in terms of the modulus, which is how far from the center point, that's nice and easy, it's just 3. And we have a rotation of 90 degrees, and we are again going in the negative direction, so our argument is going to be minus pi on 2. If you don't like writing the whole thing out, like I said, you can use our abbreviation. Instead of writing cos minus pi on 2 plus I sine minus pi on 2, you're more than welcome to just write CIS cos I sine of minus pi on 2. The HSC will accept this as a correct answer if you prefer it. Okay, and for question D, we've got a bit of a trick question because it kind of already looks like it's in polar form, except it's not. All right, for a complex number to be in polar form, the sign between your cos and sine must be positive, and we have a negative. So we're going to think about how we're going to handle this trick question. A couple of facts that are going to make this a lot easier to handle is something that you may have already covered in advanced maths, hopefully, which is that because cos is an even function, cos of a negative angle is equal to cos of the positive angle. All right, so when you substitute a negative into the cosine function, it doesn't really care, same answer. Sine, however, is an odd function. So when you have sine of a negative value, you can pull the negative out the front, and then we have sine of minus x is equal to minus sine x. All right, now we're going to do some backwards logic, and we're going to say, well, if we've got a negative right here, this expression here is technically the same thing as this. Okay, remember, if we change the angle inside the cosine to be negative, it's the same value, it's an even function. However, if we had sine of a minus angle or a negative angle, that minus sign could be pulled out the front, which would give us minus I sine pi on 3. Okay, so we're looking at this and we're looking at this and we're saying, hey, these two things are the same, okay, because of our function properties. Now, if we look at this second one in blue, because we have a plus between them, now they are in polar form, and now we can say, all right, cool, this complex number has a modulus of root 3 and an argument of minus pi on 3. Okay, so up here is not in polar form, technically. This one is. And if you want, you can again abbreviate it if you feel the need to root 3 cos I sine minus pi on 3. Okay, cool. Up next, we're going to do some practice going backwards. So here are two complex numbers that are already in polar form. We're going to translate them back into Cartesian form. If you're good with your trigonometry, this shouldn't be too challenging. Let's go through the first one. So all we really need to figure out is what the value of cos of 3 pi on 4 is and what the value of sine 3 pi on 4 is. Okay, because then we can just turn these into numbers and then we have no cos and sine. We actually have numbers, which is what Cartesian form is. Okay, we want an x and a y with an I. Okay, let's think about cos 3 pi on 4. So that's going to be cos of 135 degrees. So both of these angles are in quadrant 2. All right, we know from the advanced course that in quadrant 2, cosine is negative and sine is positive. So cos 3 pi on 4 is going to be negative cos pi on 4. Okay, so it's 45 degrees in a negative quadrant for cos. Sine, however, is positive in quadrant 2, so sine of 3 pi on 4 is the same thing as positive sine pi on 4. Okay, cool. Now, cos pi on 4 and sine pi on 4 have the same value. They're both equal to 1 over root 2. So we always want to be using exact values for questions like this, no decimals ever. Okay, so we have 6 times negative 1 over root 2 is 6 over root 2. And we have 6i times 1 over root 2 is right here. We'll leave the I out the front, so we have our real part and our imaginary part. Okay, always good manners to rationalize denominators when you can. So we'll take both our real and imaginary part and we'll multiply top and bottom by root 2. So we get 6 root 2 over 2 for both fractions, which simplifies to minus 3 root 2 plus 3i root 2. So a real part of minus 3 root 2 and imaginary part of 3 root 2. Okay, so going back from polar to Cartesian is just doing a bit of trigonometry from the advanced course. Okay, question B is a little bit simpler because we have a convenient angle of pi on 2. If we think about what a modulus of 3 and an argument of 90 degrees looks like, you're going to be thinking of this right here. Okay, 3 from the origin, rotation of 90 degrees, which means we don't have a real part. It's a purely imaginary number. It's going to be 3i. So there you go. Sometimes if you draw a picture, it does make it a bit easier. With question A, if you wanted to, you could have drawn this picture and done some trigonometry to get your answer if you find this confusing. But anyway, let's kick on. Okay, example 3, we've got 2 complex numbers and we want to find the distance between them. Okay, so our approach for this one is we are going to attempt to find a vector or a line that links Z and W, and then we're going to find the length of that complex number. So if you were paying attention in the last video, how do we find a vector going from Z to W? If you completed the assigned exercises, you probably know that Z minus W will be the vector from W to Z. Okay, so if we subtract the 2 complex numbers, we will get a vector going between them from W to Z. All right, then once we've got that complex number, Z minus W, if we find the argument of it, the modulus of that complex number, that will be the length of the vector, so we will find the distance between the 2 points. All right, so let's do Z minus W, so 1 plus 3i, take away minus 2 plus I. Works out to be 3 for the real part and positive 2 for the imaginary part. Okay, so 3 plus 2i represents the vector between Z and W. Now we're just going to find the length of this number by finding the modulus. Okay, so we take the real part and the imaginary part, we square them and we plus them together. Okay, so keep in mind, we're not squaring 2i, we're just squaring 2. Okay, we're doing Pythagoras, not some weird imaginary thing. All right, we get 9 plus 4, so we get 13. So our answer is square root 13. So these 2 complex numbers are root 13 units apart on the Argand diagram. Okay, up next, before we do a few more examples, I want to talk very quickly about what is called the triangle inequality, okay, which relates to vectors and vector lengths. So here we have a triangle. This longest side right here has a length of 10 units. This short one on the left is 4 units long, and this one here is 5 units long. Now, a very simple question for you is, do you see any problem with this triangle? Do you see anything wrong with it? Have a look, have a think. Okay, if this triangle upsets you, it should upset you because it is actually impossible to make a triangle with these lengths. Let's think about this vertex on the left and the vertex on the right. What is the shortest distance between these 2 points? Well, in geometry, we know the shortest distance between 2 points is the straight line between them, which is the 10. So how is the 4 and the 5 the shortest path from here to here when 10 is the direct path and that's longer? If you try and build this triangle, this is what you get. The 4 and the 5 can't meet up because they're too short because of this longer side right here. So what we get from this is a property that is not really talked about much in New South Wales high schools until you get to this stage. It's called the triangle inequality. It basically just says that any side of a triangle can't be longer than the other 2 sides plus together. Okay, so because 10 is bigger than 5 plus 4, this triangle is impossible. We can relate this to vectors and complex numbers. Here I've got a complex number W, and the length of this vector is modulus W. Got another vector Z, which has got its length of modulus Z. And if we stack the 2 vectors one after another, the final point here is going to be the result of Z plus W. Okay, so this is us completing the parallelogram or the triangle from last lesson. We have z plus w here. Now, relating these lengths to a triangle, we can say, well, this sum, z plus w, it can't be bigger than w plus z, because again, you would be making an impossible triangle. We get this relationship right here. It's called the triangle inequality. You see it come up from time to time, and we'll probably be proving it at some point in this course, rather than just looking at it geometrically. So yeah, modulus of z plus w is always less than or equal to z plus w. And if it was equal to, we wouldn't have a triangle, we'd have a straight line, which we'll look at later in greater detail. Okay, cool. Let's talk about how to multiply and divide complex numbers using polar form. Okay, so for adding and subtracting complex numbers, which is what we've been focusing on last week, it's easy to do that in terms of vectors. However, multiplying and dividing, it's much, much simpler to do it in terms of polar form. So here we have two complex numbers, z and w. Z has a modulus of r and an argument of theta. W has a modulus of s and an argument of, I believe that's called phi. Let me check that. Sure, phi. Okay, cool. So if we wanted to find the product of z and w, so we multiplied these two complex numbers together, the shortcut we can take in polar form is that the result is actually going to be the product of the moduli. Okay, so we multiply the moduli, and the arguments are going to actually plus together. Okay, so multiply the moduli, add the arguments. If you want to see this in terms of a diagram, I found this one really useful. So here we have z and w with length r and length s. This zw here is going to represent their product. Okay, so the lengths are multiplying together and the arguments are summing together to make theta plus phi. Okay, so a very handy shortcut, a very similar one for doing quotients of complex numbers. So if we wanted to do, for example, z divided by w, the modulus of this number will be r divided by s, and the argument will be the difference, so theta take away phi. Okay, this is one of the main reasons why we love polar form, because yeah, it makes multiplication and division super, super easy. Okay, let's have a go at some examples using these properties to multiply and divide complex numbers. So here we have two complex numbers. We've got z has a modulus of 4 and an argument of pi over 4, or 45 degrees. And w is another complex number. It's got a modulus of 8 and an argument of pi on 3. Okay, first thing we're going to find is the product of z and w. So as we saw on the previous slide, to find our modulus, we're going to multiply 4 and 8 to give us 32. To find our arguments, when they are multiplying, we're going to add them together. So if we do pi over 4 plus pi over 3, well, a quarter plus a third is 7/12. So we're going to have 7/12 of pi as our arguments. Once again, 4 times 8 equals 32 as our modulus. There you go. Super easy, super convenient. If we were doing w minus z, we're doing very similar. We're going to do the modulus of w divided by the modulus of z. So 8 divided by 4 would give us 2. For our arguments, we're going to do the argument of w, which is pi on 3. We're going to subtract pi on 4, which will give us pi on 12. So we have 2 times cos pi on 12 plus I sine pi on 12. There is our quotient. Okay, for question C, we are doing the complex number w multiplied by I. So we saw from last week's video that multiplying by I is going to rotate us clockwise by 90 degrees, or pi on 2 radians. It's not going to change the length of our vector. Our modulus is still going to be 8. But for our argument, we're going to do pi on 3, and we're going to add pi on 2 because we are rotating an extra 90 degrees. That gives us the complex number, 8 cos I sine of 5 pi on 6. Okay, so 5 pi on 6 is pi on 3 plus pi on 2 for our 90 degree rotation. For question D, we're doing negative z. Again, we saw this last week. Negative z is going to rotate us, rotate us 180 degrees, which is like reflecting through the origin. So this blue line has a length of 4 and an argument of pi on 4. What would the argument of this red line down here be? Once again, the length is still 4, it hasn't changed, but our angle has gone from positive 45. Now we're going in the negative direction, and we'll have negative 135. aka negative 3/4 of pi. Okay, so 1/4 that way, 1/4 there, and 3/4 this way. So there's our complex number, 4 cos I sine of minus 3/4 of pi. Okay, for E, we have W conjugate. As we saw before, the conjugate of a complex number is a reflection across the real axis. So we started off with an argument of pi on 3. Now we're going in the opposite direction, so we'll have an argument of negative pi on 3. Once again, modulus length has not changed. It's still going to be 8. But our angle has gone from positive to negative. Okay, and for the final one, z squared. So we're going to take the complex number z and we're going to multiply it by itself. So its modulus is going to be 4 times 4, gives us 16. Our argument is going to be pi on 4 plus pi on 4, which gives us 2 pi on 4, which is a half pi. So we've gone from 4 cos sine pi on 4 to 16 cos sine pi on 2. We'll be doing more work on powers of complex numbers next week, but that's just a little intro to it, I suppose. Okay, let's finish off today's video with an HSC question from 2006, ranging from bands 3 to 5. I like this question because when you first look at it, it kind of looks a bit complicated, but once we work through it, I think you'll find it very achievable. Okay, if you're feeling brave, of course you can pause and have a go yourself, but otherwise I'm going to go through it like now, I suppose. Okay, part I. We've got the complex number 1 plus I root 3 divided by 1 plus I. We want to write this in the form x plus iy, where x and y are real. We've done questions similar to question I already, where we have a fraction of complex numbers and we're asked to write it in x plus iy form. The way we do this is we multiply top and bottom by the conjugate of the denominator. Okay, so if you want to stop there and try yourself, here's how we do it. So 1 plus I root 3 over 1 plus I multiplied by 1 minus I on top and bottom. Okay, conjugate of the denominator. So up top, we'll get 1 minus I, and we'll get I root 3 minus I squared root 3. There's our binomial expansion for the numerators. For the denominator, we get a difference of squares, 1 squared to take away I squared. Okay, as always, when we see an I squared, we're going to replace this with a negative 1. So on the bottom, we'll get 1 minus minus 1, which is 2. Up top, this is going to turn us into a positive root 3. I'm going to put that at the front with the 1, so we have our real components together, and we'll put our imaginary parts together. Factoring out the I gives us root 3 minus 1 for the imaginary parts. Okay, so tidying up the top, reals and imaginaries all over 2. Now we want to write this in x plus iy form, so we want to split apart the real part and the imaginary component, which is going to look like this. So we have 1 plus root 3 over 2 for our real part. For our imaginary part, we have root 3 minus 1 over 2. So there is our x and there is our y. So we've answered the question because those two, even though they're not rational, they are real numbers. So there's your 2 marks. Okay, we'll keep that aside because that's going to come in handy later, that this is the Cartesian form of this complex number. Now part 2, which is worth 3 marks, which is most of the question. By expressing 1 plus I root 3 and 1 plus I in mod arg form, which is what we call polar form now, write 1 plus I root 3 divided by 1 plus I in mod arg form. Okay, so now it's a chance for you guys to pause and have some practice at turning this complex number and this complex number into modulus argument form, aka polar form. See how you go. Okay, so 1 plus I root 3, if you do a little sketch and do a bit of trigonometry, you should see a modulus of 2 and an argument of 60 degrees, which is pi on 3. If you do the same thing for 1 plus I, you should be seeing a modulus of root 2 and an argument of pi over 4. Okay, sweet. Now, how are these two facts going to help us get 1 plus I root 3 divided by 1 plus I in mod arg form? Well, we already have the top and the bottom in mod arg form. And how do we do the division of two complex numbers? We've already done that in the previous examples. So we can do 1 plus I root 3 divided by 1 plus I. We can do that by dividing the moduli and subtracting the arguments. Okay? So we're going to do 2 divided by root 2, and we're going to do pi over 3 take away pi over 4, as we saw previously. Okay, so here is our division of this complex number divided by this complex number. 2 divided by root 2, and we have cos and sine with pi over 12 because that is a third, take away a quarter. All right, sweet. Now we can write 2 divided by root 2 as just root 2 if we simplify that fraction. And so now we have a complex number has a modulus of root 2 and an argument of pi on 12. So there is your 3 marks, final answer. Okay? They gave you the hint to get these two in polar form, and that makes getting your answer really simple and straightforward if you know your content. Okay, and for part 3, so putting those two aside for now, we have hence find cos pi on 12 in surd form for 1 mark. Okay, so here's what we achieved in part I of the question, and here's what we achieved in part 2 of the question. How can we combine these two to get an expression for cos pi on 12 in surd form? Well, keep in mind that the left up here is the Cartesian form of this complex number, and over on the right we have the polar form of the complex number. However, these two are equivalent. They are just different forms for the same complex number. So we can say that our answer from part I is equivalent to our answer from part 2. Okay? Now, as with any complex number, if we have two complex numbers that are equal, it means that their real parts are equivalent and their imaginary parts are equivalent. From this, we can say 1 plus root 3 divided by 2 is equal to root 2 times cos pi on 12. Okay, so real part equal to real part. Now we can just divide both sides by root 2, and now we have cos pi on 12 in surd form. Given this is a 1 mark question, that would probably get you a full mark, but it's always good manners to leave your answers in rational form in terms of the denominator. So good habit is to multiply top and bottom by root 2. And so we end up with root 2 plus root 6 over 2 times 2, which is 4. Okay, so there is probably a full marks answer, but there is a better answer as a good habit to try and build. Okay, excellent. Thanks so much for watching. Here's some assigned work for you guys to get some practice with. So there's exercise 1D in Cambridge. If you want some more practice, Howard's got some good questions in exercise 2.3 as well. So you can pick either of those, or if you're really keen, you can try both. But please let me know if you need any more help, and thanks for watching this lesson. See you later. Bye.